Good afternoon from Bangladesh. This is the 48th lecture of AS and A-level chemistry. And we are talking about analytical techniques. And in last lecture, we talked about proton NMR and carbon-13 NMR. And we also mentioned how to interpret the NMR spectrum. And we were talking about various aspects of how we made the solution and the chemical shift, how we looked to the chemical shift, how we looked to the environment of molecular environment. This is what we are talking. But to continue this, today we will take a few very subtle point of interpreting the spectrum of molecules. Here we will see in this slide that carbon-13 NMR spectrum of propanon. And here is the propanon molecular arrangement, the molecular formula of propanon. And now we have to interpret this. Well, first of all, we have to look into it that what is the solvent we used for taking the NMR spectrum of propanon. And in many cases, almost all cases, when we take carbon-13 NMR, we use CDCl3, that's what we have mentioned, to take the NMR spectrum and dissolve the molecule in the CDCl3. Okay, once we dissolve the molecule in CDCl3, we also get a peak for CDCl3. And that peak is around 90 ppm. Okay, so around 80 ppm, sorry, around 80 ppm. So we will be ignoring the peak of CDCl3 while interpreting our NMR spectra. Okay, so if we this is a spectra, and if we would not know that molecule, how would we interpret? First of all, if you remember, we were talking about table which is available, his library of NMR spectra, and from there we start looking for how many peaks we have in the spectra, and then what is the shift for that spectra. That's what we have to look for. Okay, as I said, 88 will be the signal peak for CDCl3. Here we see 88, the signal peak of CDCl3. To make it's a simple spectra. To make it very clear, what we do, we ignore the signal of solvent CDCl3 while analyzing the spectrum. Okay, so and then we go for the library and find out the what would be the peak for 200 and what would be the peak for chemical shift for this one. And if we find the chemical shift of this one and chemical shift of this one, and then we compare the library and look for the compound. What is this? Let's say this is a propanon. What is this? How many peaks we are supposed to get? We have 1, 2, 3 carbons, so we must get at least 3 peaks, is it not? But then we see here it is only 2 peaks. What for? Why? Because we look for the molecular environment also. So this CH3 and this CH3 is having exactly the same molecular environment. So for these and this CH3, we will get 1 peak, and that is this one. Okay, And we compared it with the library and find it this should be the peak for CH3 and CH3. Okay, and then another carbon we have, that is carbonyl group, and then you see this carbonyl group has got different molecular environment, not like this one and this one. This is a different molecular environment, and we should get a peak for that different molecular environment. So in fact, in this molecule we would have got two peaks, and if we say 3, then including the solvent CDCl3. Okay, but this is 200. Okay, then that's what I have analyzed here, and then we are taking another compound or another spectrum, and you see again that spectrum, look to this, and that spectrum is the molecule is dissolved in CDCl3, and therefore we are getting a peak here. And once I said that to make it more easy, we ignored the peak of solvent, so we'll ignore it. Then how many peaks do we have? It is what is it? Ethyl benzene. So you see, this carbon has got a different environment than this one, or this one has got a different environment to this one. So we would have got 2 peaks for this ethyl group. And then if we look to the chemical shift, we see that for CH2, this is the peak, and for CH3, this is the peak. Okay, we have also benzyl group, or ethyl benzene, what do you say? So, and benzyl group, this carbon, the 6 carbon, they are equivalent. The carbon atoms in the benzene rings are almost equivalent, but will be affected to slightly different extent by why slightly different extent, why not 1 slightly different, because the presence of ethyl group, and that peak for ethyl is in the chemical shift 130 to 120 ppm. Okay, we go for the next slide, and then we see that next slide, what we see that we have to predict, let's say we have to deduce the ibuprofen, what would be the peak, number of peaks, how many peaks we would expect to get for ibuprofen. So what do we do then? The first step, we take the molecular formula of ibuprofen, and that is what it is, C13H18O2. Okay, then we expect at least 13 peak in the spectrum if all the carbon atoms are environmentally different, not equivalent. But when we next step, what we do, we go for the skeletal formula of ibuprofen and find out, this is the skeletal formula of ibuprofen, and find out how many what are the carbon atoms in here which are non-equivalent or environment is different. So if we look to this, we will see that there are different, we have at least instead of 13 peak, we get 9 peak, and these distinct peaks are of different environment. Therefore, 9 peaks, for this 9 peaks, we get the different 9 carbon environment carbon atoms. We should get 9 peak instead of 13 peak. And if we go through the library and find out the carbon 13 NMR spectrum, we will see that there are 9 peaks. Yeah, you see 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks. There are 9 peaks. So that's how we deduce, or we predict the spectrum of a organic molecules, carbon 13 spectrum or proton spectrum of organic molecules. Okay, we have next slide. What we have? Well, we are talking about high resolution NMR. Why we have to go for high resolution NMR? Because the chemical shifts are given over a range. Yes, over a range, and the range of different types of hydrogen atoms do overlap. In some molecules, there are heavy shielding of hydrogen nuclei by lots of electrons in surrounding atoms. Peaks are shifted beyond their usual range. Because of this, peaks are shifted beyond their usual ranges. In such cases, high resolution NMR is useful. If we met this, what we said a bit earlier, we need high resolution NMR to solve that. High resolution NMR gives us more information to interpret. We will see the peak which shows one signal on a low resolution NMR that is revealed and to be made up of a cluster of closely grouped peaks, and that what we have to go to this table and see, which shows, this table shows number of signals as peak splits into n plus 1. This n plus 1 called n plus 1 splitting rule. What we see in this table, we see that this column, we are looking for number of adjacent hydrogen atom, and that this is a splitting pattern using n plus 1 rule, and this is relative intensities in splitting the pattern, and this is observed on the NMR spectrum S. So if we do not have any hydrogen atom, so hydrogen atom n is 0, so we should get one peak, and if n is 0, then 0 plus 1, we should get one single peak, and that's what we call singlet in high resolution NMR spectra. Okay, relative intensity is 1, and that is the singlet. If we have the adjacent atom has got one hydrogen atom, then n plus 1, 2, and then we should get a doublet, and the relative intensity is 1:1. This is what we are getting for doublet, you see, doublet. Okay, if we would have a adjacent hydrogen atom number 2 adjacent hydrogen atom, then using this n plus 1 rule, we should have at a peak 3 peaks, which you call triplet, and the relative intensity 1:2 is 1. Let's see here, 1 is here, and then 1 is here, and this is double intensity 2, and then again 1. If we have 3 hydrogen atom in the adjacent atom, 3 hydrogen atom adjacent, now 3 hydrogen atom, then 3 plus 1, it is 4, then we get 4 peaks split into 4. The peak cluster is split into 4 peaks, and it's called a quartet, and the peak shows like this, that you see 1, intensity 1, and then 3, and then 3 again, and 1. This is how splitting we will see. So this splitting of nuclei, we call it spin-spin coupling. The exact splitting pattern of peak depends on what? On the number of hydrogen atoms and the adjacent carbon atoms or atoms. Okay, so number of single peak splits into n plus 1, and that's what we call n plus 1 rule, as I said, in NMR spectra. So what we can now taken examples of high resolution NMR of spectrum of ethanol. This is a high resolution NMR spectrum of ethanol. So this one is definitely a standard. We are using a standard, and then what we see that here we see a triplet, here we see a doublet, here we see a singlet. And how we explain this? We can explain the CH3 peak splits into 3 as it has got an adjacent atom 2 hydrogen. So 2 plus 1, it splits into 3. There we get the 3H. So there we get the 3H. And then we have see this one. This we call it triplet advisate, and the 3 CH2 peak is split into 4 because it's adjacent. One is CH3, and there are 3 hydrogen, and therefore it's split into according to n plus 1 rule, it's split into 4 quartet. I would say it's split into quartet. Here it is the quartet. If you remember that this quartet, it's quartet. And then the OH, we have gotten OH, CH3, CH2, OH, is it not? So the OH peak has no split on its hydrogen atom to corresponding, because it's exchanged the OH atoms over other ethanol molecules or any water present in it. So this results in average peak, which is 1 peak and 1H. That's what is this splitting. Okay, we'll go for the next one. Well, this is a problem. We got a NMR spectra, and it is said that is an ester, and we have to identify which ester it is. That's what we have to identify. And now, what we look for, where are our where are the peaks? We do get 3 major peaks. Here is one, another one, another one, with splitting. You do remember with splitting. This is a high resolution NMR spectra of an ester, high resolution. So we will get splitting also. That is what we talked about, n plus 1 rule. We do get n plus 1 rule here also. So using the table, we get the chemical shift to 1.3. This one is about 1.3. This one 1.3, and for 1.3 ppm, it could be RCH3 or RH2 or R2H. And chemical shift, we have 2.2. For 2.2 chemical shift to 2.2, we possibly get CH3CO or RCH3CO or R2CHCO. And for 3.9, this one is 3.9, and for 3.9 ppm we get this. And usually the relative number of each type of proton, labeling each major peak to narrow down possibilities. So 1.3 ppm labeled as 3H, so could be the RCH3. 2.2 labeled as 3H, so could be CH3CCO, and 3.9 ppm labeled as 2H, and so could be OCH2R. So by applying the n plus 1 rule and getting for the singlet and also triplet and quartet, and then what we do, we put this information together and we find this the ester would be ethyl ethanoate. Okay, we go for the next slide, and here we are talking about labile protons. You know, we do observe hydrogen bonding in organic compounds in many cases because of highly electronegative oxygen or nitrogen bonded. For example, we take this one as an example, and you see that this is an ethanol, and therefore this is a very this oxygen is having a high electronegativity compared to this hydrogen, and therefore they have bonding, and then we call this hydrogen bonding. So the hydrogen bonding could affect this spectra. So how to look at whether this hydrogen is labile hydrogen or hydrogen of the ethyl or methyl group or so, or aryl group. That's what we are looking for then. So we have to distinguish between labile proton and the proton and the molecule. So if it is labile proton, it can always jump from one molecule to another molecule and so forth. So therefore, labile protons do not couple with the protons linked with neighboring atoms. This means the NMR peak for a proton in the OH group appears as a single peak in high resolution molecule. So what are the techniques that we can use for identifying labile protons in NMR? So we take deuterium oxide. We take the spectrum in presence of deuterium oxide. Deuterium oxide, you know that is heavy water. So if we take spectrum of deuterium oxide, the nuclei can exchange rapidly with the labile protons, and deuterium nuclei do not show up in the proton NMR region or of the spectrum, and so these peaks of the labile protons will disappear. If we use deuterium oxide to collect the NMR spectrum, and we will see that the peak for labile protons disappears, and there we will use to identify whether it is labile protons or not. Okay, this NMR we are talking, so far we have been talking about NMR technique for identifying specifically organic compounds and their structure and molecular structure and unknown compounds. But this technique can be also used in medicine. And nowadays you do have heard probably that MRI. The MRI, can get information of human bodies, hydrogen nuclei in human body, or especially in water and lipids. So with the help of MRI, we can find out the soft tissues in internal organs, which normally we don't get while by going through or taking X-ray. So that is what we MRI, I mean magnetic resonance imaging, we do for human body and find the tissues and can explain interpret whether the organs are okay or we have some sort of some sort of tissues, etc., which is not functioning properly. So in medicine we do use very much magnetic resonance imaging. This is the technique used for, as I said, in medicine, surgery, etc. Well, one thing we have to also say that there is chemical shift at typical values of very many different solvent and concentration of substituents present. So we can get chemical shift a little bit varying. Why? Because of what sort of solvent we are using and what's the concentration and what substituents are present. This is a table which shows that the chemical shift we expect for carbon type. So if it is sp3 hybridization, that is alkyl hybridization, that means the examples are structure example CH3, CH2, CH that have got a chemical shift 0 to 50. Okay. Similarly, if we have sp3 hybridization of carbon atom, then next to alkane or arene, so this is what is next to alkane or arene, we will get a shift, chemical shift 25 to 50. Okay, that is what I mean the chemical shift, which typically values can vary slightly. So you can see in this table, this column, the carbon atoms hybridization, sp3, 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 and sp2, and then again sp2, sp2, sp nitrile. That if compound like this, the chemical shift could be from 100 to 125. Okay, we go for the we talk now a little bit about this 48 lectures we have arranged, and I did it in my mind that this might help the AS and A-level student while preparing for their exam. And what I have done, I have taken the syllabus of Cambridge and Edexcel of AS and A-level chemistry, and tried to prepare in total 48 lectures. I hope very much with the help of textbooks and slightly reduced, of course, main chapters are there, and slightly reduced and slightly explained a little bit more, so that the student of AS and A level can understand the basic chemistry of A level. I hope some of the students, if go through these 48 lectures, could have a good knowledge of handling the questions of AS and A level. Good luck to you. Thank you very much. And this is the last lecture I delivered for AS and A level chemistry. Thank you all.